everyone. Welcome to our first workshop for the day. Thank you for your patience. I'm Samantha from SG Innovate's talent networking team. And at SG Innovate, we develop talent capabilities for the deep tech sector. Our first workshop for the day is Introduction to Artificial Intelligence, Kickstart Your Career in AI. In this 1.5 hours, we want to debunk some of the misconceptions behind AI, the exciting things you can build with deep learning, and show you the skills and tools needed into the world of AI. Now, it is my pleasure to introduce to you our trainers for today, Dr. Martin Andrews and Sam Witteveen, co-founders of Red Dragon AI. Now, Sam has over 20 years experience in machine learning, and Sam has used machine learning in AI to help build B2C companies with more than 1 million users. In 2017, they were both appointed by Google as one of the first Google developer experts for machine learning in the world. If you have any questions throughout the workshop for either of them, please feel free to use the Q&A function or the chat function within the Zoom link, and we'll address them at the end of the workshop. Now, without further ado, let's welcome Martin and Sam.
Thank you. All right, I'll kick it off. All right. We can get this going. All right, so I'm going to be talking about finding your path into AI and deep learning. We're sort of approaching this whole sort of thing as looking at it, a lot of people are looking to change careers into deep learning. So we're going to be talking about some opportunities, and also talking about, some of the things that you can do with this kind of thing. So a bit about myself. I'm a Google developer expert for machine learning and deep learning. Along with Martin, we are both co-organizers of the Singapore TensorFlow and Deep Learning Meetup. We have about 4,500 people in that meetup now. We've been doing it for the past 3.5 years. And also, I tend to work in deep learning related to language and dialogue systems and generative models as well. Along with Martin, we're both co-founders of a startup called Red Dragon. This is not my first startup. I've done multiple startups before. But Red Dragon is very interesting in that we're doing stuff related to deep learning, a whole bunch of things around prototyping and research. We also do some education courses with SG Innovate and other places around the world. And we're a Google partner. What we sort of tend to focus on are things related to conversational AI, natural language understanding, and a whole bunch of things to do with sort of graphs and stuff like that. So let me get started. For the goals for this talk, for both of what Martin and I are going to both talk about, is sort of show you some of the things that can be done in AI, to sort of convince you that it's not as hard as a lot of people are making out, to help you get started with some resources and things like that, and to show you that this could be a new career for you. So if you're looking, you're at a stage in your life where you're looking to change careers and you've got a certain skill set, this might be a good career move, for you as well. All right, so let's start off with what is AI? So this is a really fundamental question that you don't see a lot of people talking about. In many times when people are using the word AI, actually what they're talking about is just a marketing term. So a lot of things that are being called AI out there are actually, quite fake, or certainly not very intelligent learning systems to them. The sort of more classical definition of this would be, AI is to make machines solve problems that are commonly associated with human intelligence. Right? And more fundamentally than any of this is that really AI is what's getting the biggest breakthroughs in nearly any field these days. This is something that we see time and time again when we open the news, when we look on social media and stuff. People are talking about new things that can be done. Often there are elements of AI and also of sort of deep learning. So I'm going to start off with a little slide from Google, some concepts from Google. So AI, at Google, for the past couple of years, Google has talked about that they're in this first AI first world and sort of positioning themselves as an AI first company. So to think about that, previously to this, Google was a mobile first company, meaning that they focused on trying to deliver as much as they could to mobile users and mobile devices. In the past few years, though, they've changed to AI first. And I think it's interesting to look at what they sort of think of is important in this AI first world. So one of the first things and key things at Google is this idea of things being conversationally and sensory based. So as you're starting to see, things like Google Assistant, even things like Alexa or other, Siri to a maybe lesser extent, are becoming the norm for the way a lot of people interact with computing. The other big one that we're seeing is sensory-based things. So where once upon a time it was very expensive to make sensors, now we can make sensors for just, often even under $1 and have so many of them that can be measuring things in the world. And this allows us to have this sort of multi-device or sort of ambient computing, which is all around us. And what comes of that is that whereas with mobile first, you generally only had a few contexts that you could think about. The biggest one was your location. So obviously in mobile phones, once they got GPS, that enabled businesses like Grab, like Uber, it enabled all the food delivery apps, that kind of thing. But with an AI first sort of perspective, there are lots of different contexts that we can start to think about. So we think of this being thoughtfully contextual. And the idea is that these systems can learn, adapt, and personalize to the user themselves. You're seeing this, every time you open YouTube and you're seeing, recommendations that are just for you. Even Google search now is different for every user around the world. So as these things get better, they sort of learn and adapt to your particular situation. So what's driving this? Well, I'm guessing most of the people on this call have already heard of the concepts of machine learning and deep learning, and this is what's basically driving probably 99% of all the AI breakthroughs that we're sort of seeing nowadays. So this brings us along to what is deep learning. So this is what the media thinks. So these are two pictures that were sort of taken out of publications when they were talking about some of Google's new algorithms that they had introduced. The media often likes to portray AI and deep learning as something being that's going to take over the world, that it's evil, that it's the Terminator, that kind of thing. Unfortunately, we're nowhere near the level of sort of sophistication as the media would have you believe for some of these things. What most people tend to think of is the idea of that we're sort of building brains. And this is also a fallacy in that really what we're building, is really at the end of the day, mathematics and different, forms of mathematics to produce results. But there's some nice analogies to the brain. And this is how this idea is sort of taken off around the world. So if you think about, this sort of big sphere of AI, inside of AI, you basically have machine learning, which is sort of like, a subfield of that. And then inside of machine learning, and machine learning is not new. All these things here have been around for quite a long time. And inside the field of machine learning, you've got what we call neural networks. Neural networks themselves, have been around since the 1980s, some versions even before that. And then the thing that sort of sits in the middle of all of this is deep learning. So this is machine learning using deep neural networks here. And the idea here is that whereas the first three had been ideas that had been around for a long time, nobody really managed to make these things quite deep. So they were very surface level sorts of things. But in the advent, in the past sort of 10 years or so, we've seen massive increases in compute, massive increases of data, and that's allowed all of this to work. So to give you sort of an idea of the depth, this is a model from about 5 years ago. And if we look over on the left here is the input, and on the right is the output. And each one of these is sort of a set or a node of computations that's going on. And this just wouldn't, this wouldn't have been possible before sort of, 5 years ago. This model itself originally used to take Google about a week to train and would cost about $30,000 in power bills and stuff like that for just training this model. The cool thing is this model now is totally, has totally been surpassed by many, many other models. This model is looking at, roughly around 20 to 30 billion parameters, 20 to 30 million parameters. The biggest models nowadays go right up to sort of 200 to 600 billion parameters. So this is something to sort of see that we're still in this massive growth period with these kind of things. Another way to think about this that I really like is this idea from Andre Karpathy. So Andre Karpathy is now the head of AI at Tesla, and he talks about this idea of software 2.0. And this is sort of like the way of thinking about this is very different than software before sort of machine learning, before using deep learning. So let's sort of look at this. So in the past, you would basically have, your data, you would write a bunch of rules, and then you would use those rules to basically generate some answers. So, this basically was determined all by how good the coder was. If you've got a really smart coder and they can write really sophisticated rules, then they can do certain things. But you can see that there are a lot of challenges here that no matter how sophisticated those rules are, they're always going to be reasonably finite with humans. In that, if I asked you to write me a program that would work out how tall is someone, you'd probably want to have like their height as the input. Maybe that's going to be the data. And then you might write something like, well, if their height is greater than 180 centimeters, I'm going to say that they're tall. If their height is less than that, I'm going to say that they're short. But you can imagine that if I asked, well, hang on a minute, is tall and short the same for gender? So do we say, is a tall woman going to be as tall as a tall man? Is it the same for age? What about a tall child? A tall 10-year-old is probably not going to be anywhere near as tall as, as a tall adult. Also for things like race, a whole bunch of different things there. So you can see that very quickly, if you were trying to write all the rules yourself, then suddenly now you've got to get a really sophisticated, program going on here. And if there are any flaws in that, that will be shown in the answers that come out. The new way of thinking is that with machine learning is that basically you pass in the data, you pass in the answers, and then it will generate the rules. So it will decide, what those variables should be that it pays attention to. So if you pass in a picture of a young child that you say is tall for their age, you pass in, a picture of a guy, a picture of a woman, it will sort of work out that related to these things, what should be the rules that it uses to determine, what makes someone tall, what makes someone short. So this sort of way of thinking is what we would call sort of software 2.0. So I mentioned before that, deep learning is a field of neural networks. It's been around for sort of 30 years plus. It's really only been viable in the last 10 years due to this more data, more compute and better design patterns. And like I mentioned earlier on, that the majority of all the sort of breakthroughs in AI are being driven by deep learning. So let's have a look at some of the things that can be done with this. So I'm going to try and look across to the questions every now and then. All right, so what can we do? Let's look at some of the things that we can do with this sort of thing. First would be classification models. So this is where we're basically saying there are two classes of things or two groups of things, and we're trying to classify something into one group or the other group. This is basically something that is probably the most common version of machine learning and deep learning that you'll see out there. So hopefully for all of you, you can look at this picture and you can say that some of these are chihuahuas and some of them are blueberry muffins. Hopefully you're good enough that you can look at one individual picture and know if it's a blueberry muffin or a chihuahua. The interesting thing is actually this problem is unbelievably easy for a deep learning algorithm to solve. It can very quickly spot the relationships between the eyes and the nose and where the, how the blueberries are put in the muffin. To be able to tell the difference between these things are really, really easy. So we got a question about, asking it, does it have to be, do we have to have a lot of data? Do we have to have it be really accurate? Of course, we want it to be accurate in that if we were telling the model that some of these blueberry muffins were chihuahuas, we're probably not going to build a great model. All right, so we need to be accurate in sort of being able to give it examples. Now, ideally we need, we would like to have as much data as possible, but of course that's never the case. And we find that you can get really good, results with often just like 100 images from each class. And that will often be with a lot more classes. Depends on how close your classes are to each other. So another type of model is also, this is also a classification model, but this is what we call segmentation model. So this is now doing the same thing, but at a pixel level. So if you see in here, it's looking at every pixel in here and it's saying, okay, is this a live traffic light? Is this a pedestrian? Is this a car? Is this, the sky? All these sorts of things. So these are the kind of models that are driving the whole of self-driving cars that we're seeing. All the advances in self-driving cars, or certainly the majority of them, have come out of what we call perception models. And these are the things that being able to interpret what's going on. Now, in this case, we're just looking at a simple image that's been segmented, but you can also have things like 3D images and LiDAR scans, and they can be dealt with in the same kind of way. Another more interesting model, image captioning models. So this is where you've basically got a lot of data and you've got captions for each image. You train up a model then over the captions and it will learn to be able to describe things in a picture. So if you look at this is a picture that the model had never seen before. And you can see that the description that it's basically said is a person on a beach flying a kite. So if you look carefully, we can't even see that the kite and the person are even connected. Yet the model has basically seen, obviously, enough examples of the beach, of the sky, of kites, and of probably people looking at kites where it's being told that the person was flying it, that it kind of works out that, okay, if the person is facing in the direction of the kite and they're looking at it, there's a high probability that they're the person flying it. Now we notice that it totally misses out the other person lying on the beach in its description. So it's certainly not a perfect description, but it is pretty amazing that it can basically look at a bunch of images and see something like this and then be able to, describe it. So these kind of models are required, you need a lot of pictures to be able to train them. You need a lot of captions to be able to train them. This is, you could kind of think about, this is one of the reasons why companies like Google and a lot of the big tech companies are quite happy to give you, free Google Photos or something like that, because it helps you, train their models to be able to do stuff like this. All right, so the next one's up are some models that I worked on about 3.5 years ago now. So these are starting to move into generative models. So if you look at the top layer here, the input to this is basically, the one on the left is the input to the model, and that's a low resolution picture. So that was about 22 by 22 pixels. The image in the middle or in the center there is what the model learned to predict this lady looked like, and then the image on the right is what she really looked like. So you can see that the image on the on the left is what goes in, the image in the center is what comes out. So this is called super resolution. And this is actually doing 8x super resolution. When I first did this, at the time, it was, the whole idea was still pretty amazing that it worked. It was sort of 3.5 years ago now. And I showed it to my wife, and my wife looked at it and said, oh, but they do that all the time on CSI on TV, right? And I had to tell her that, like, that's fake. This is real, right? This is the real thing. So this sort of shows what you can do with, very low resolution images and do the same, be able to, supersize them and upsize them there. The one below that is going to be a colorization model. So this is basically doing it's actually the same kind of model. Except because we're doing an image in and an image out kind of model. So we're not predicting anything about the image, we're just manipulating the image with one of these algorithms. In this case, we basically train it on black and white images, being the one on the left, color image being the one on the right, and then it learns to be able to predict. So this is an image that it didn't see in the training, and it was able then to predict this image in the middle. Now this image in the middle, you'll notice that the lighting in the background there is different, right? That it's actually fixed up the lighting there. So the lighting in the background you can see is like what we would call warm lighting. The model has seen so many images, it's seen a few 100,000 images at this point, that it's able to be able to fix that up and correct that as it goes through. And this is one of the advantages. This kind of model is pretty much in every modern day phone nowadays. Whether you've got an iPhone or an Android phone, they're using these kinds of models, as long as you've got a reasonably recent one, to do a lot of things for photography and fix up images and stuff. Another example would be OCR. So this is something I worked on last year. This was basically taking Thai ID cards, and you can see that they weren't, always very clear, and we were able to extract out the image of the person, extract out the person's name, extract out their details, and also be able to sort of predict if they're, if they're female, if they're male, do a whole bunch of things like this. So this is sort of the first step to doing sort of normal sort of full-on OCR. So this actually requires 3 different models to do. Another version of this was doing it with handwriting. So this was sort of an attempt to basically come up with something that could do Thai handwriting and take different forms of handwriting. You can see that each of these is quite different, from some being quite neat to some being really messy, and then train a model so that it could actually go through and read these and work these out. And I've just touched the surface here. There's a whole bunch of these different kinds of models out there. So there are other ones like neural machine translation, object detection, speech recognition, question and answer systems, whole bunch of different sort of artistic models, not to mention things like recommendation systems, anomaly detection, and stuff like that. So let me talk a little bit about Google and just sort of explain the explosion that we've sort of seen over the, over the past sort of 5-6 years. So this is actually quite an old slide now. This shows that the graph there is showing inside Google how many directories were containing deep learning models in them. And so Google has its sort of own internal repository system, kind of like its own internal GitHub. And in there, how many folders actually contain deep learning? And you can see that sort of around about, the start of 2014, it really started to pick up. You can see by 2015, it was starting to explode. And, by 2016, and the graph has now gone to well over double this, pretty much now every Google product has machine learning or deep learning in it in some way, shape, or form. Whether we're talking about, YouTube recommendations, Google Play recommendations, whether we're talking about Android and the speech recognition going in there, Google Translate has a whole bunch of things to do with machine learning and deep learning, right through to things like Gmail. So if you're using, the Gmail Smart Reply, that's basically a deep learning model that is reading the email and then predicting the 3 best replies that you can choose for one of those to just click and be able to answer an email quickly. So all of these products are using not only machine learning, but now also using deep learning as well. So this has sort of become huge in the past 5 years inside Google. But it's not just Google, right? This is one of the things that we kind of want to stress is that, in many ways, Google was just the tip of the iceberg in that they were there early, they learned some of these things and applied them very quickly. We're seeing now in every industry, these techniques are starting to take off. So computer vision is being used, for example, for detecting things in pictures, describing things, looking for similar images, analyzing health scans, radiology scans, all those sorts of things. But doing simple things like quality control. So in one of our courses that we just taught recently, we had one student who was working at a solar panel manufacturer, and he was able to basically build a model that could find flaws in solar panels, from doing this kind of thing. Now, this sort of brings into one of the things I'm going to talk about a bit more, and I think Martin will also talk about this idea that, often having some domain expertise plus the deep learning is what gives you state of the art. So we certainly didn't, know anything about solar panels, but we were able to teach him about the deep learning stuff. And from that, he was then able to apply the knowledge that he knew to basically make this work. And it's not just, it's not just computer vision. We've got structured data models for things like predicting sales and prices of things, for helping with budgets, for making recommendations. Anytime you use Amazon, anytime you're using, any sort of high-end e-commerce provider, they're making recommendations all the time on the data that they know about you to predict what you're most likely going to buy. And then a whole bunch of different healthcare outcomes. This is becoming a huge industry that's starting to use deep learning a lot as well. Text and natural language processing. So Martin's going to show you some really cool examples of things that come with text. But there are a whole bunch of things like, analyzing sentiment, classifying emails, customer service tickets, chatbots, all of these things when you basically are doing this kind of thing. So I see someone's asking me, is it useful to use AI in 4D or for gambling predictions? So good question, right? It's not going to be useful probably if the outcome is 100% random. So maybe for 4D, that's not ideal. But there have been examples of where Russian hackers have basically been able to sit in front of slot machines in Vegas, film them for a certain time to work out what the random number generator is, and then use a machine learning model to predict which machine they should be betting on to get the highest return. So, that maybe that's not totally legal, but that was one of the things that, people have used. Anyway, my point being that, almost any industry that you look at now, we're starting to see these models being used. So another thing that, a lot of people get sort of stuck up in is thinking that, oh, I need to be a genius to do this because it's all about research and stuff like that. One of the big things that we want to say today, and Martin will certainly talk more about this than myself, is that industry needs implementers. Industry at the moment needs, people out there who know how to implement these common techniques for specific industry applications. And if you're someone who's had a career in a particular industry already, and you know the key problems that they have, the big challenges that they're having, you often have a really good advantage of being able to learn the deep learning and know where is best to apply it, and be able to use that as a really good skill set. But we like to say that, deep learning plus domain expertise equals state-of-the-art results. And this is, something that you're sort of seeing. I can give you some more examples from Google. Google obviously nowadays has branched out into lots of different companies, some of them related to health, some like Waymo related to self-driving. And generally what they're doing for most of those companies is teaming up domain expertise plus machine learning and deep learning and technology expertise to create some sort of state-of-the-art result there. All right, so let's look at how this stuff works. So there are 4 major building blocks for building these kinds of things. And I'm going to go through this reasonably quickly. When we teach a course, we go through this quite in depth, but I kind of feel like in a very short time, you can get the idea that some of these things is not as hard as you seem. So when we're building a model, we're going to basically have the inputs, and this is going to be like for example, the pictures and then the labels. We're then going to pass it through what we call an architecture, which is going to be some form of compute. We're then going to measure how, the answer that came out, and we're going to take a loss of that answer, and then we're going to use an optimizer to basically update these sort of architectures and hidden layers in there. So that's all it is. And then by doing this and running this, this multiple times through, we're able then to, produce results out. So this is another diagram of the same thing. I've just broken it out so that you can see that in each of these architecture layers, there's a whole bunch of what we call weights and biases. They're just variables. So just like we had, in the model about being tall, where one of the things might be if they're above 180 centimeters, this is where the rules are being made, but they're not manually made by us. They're made by this algorithm going through and working out how to update this as quickly as possible to get the results that you want in a way. And you'll do it with, usually thousands of images or, lots of different text, that kind of thing. So model inputs, everything needs to be turned into a number because at the end of the day, we're basically just talking about, we're talking about numerical math. So things need to be turned into a number. So we have sort of what we call vectorized data, which would be continuous or categorical. We have images, which are things like, just a digital image. It's basically got 3 channels, red, green, blue. And that's just a bunch of numbers, so we can pass that in. We've even got things like, sequences, where we can turn text and words into numbers and have lookup tables for going back and forth between a word and a number, and then going back as it comes out of the model from the number to the word as we go through with these things. Second thing is we've got the architectures. So this is the bit where people start to sort of think, wow, this is hard. And really the thing is, there are a limited number of key architectures that we talk about. So there are sort of 4 main architectures, and these are just design patterns for doing connectivity things inside the model. How do you connect all that data up and wire it up inside the model? And it turns out that some of the models lend themselves to types of data much more than other models. So for example, if we want to work in images, we would be generally focused on convolutional neural networks. If we wanted to work in structured data, we might focus more on fully connected networks. If we wanted to work in text, we'd probably look at these two, the recurrent networks and the transformer networks. So this is something that you would gradually learn over time. You can think of the architecture as like an engine of the whole thing, that it's basically what's getting fine-tuned as we're putting the data through it, it's getting updated and fine-tuned to produce the result out that we want. We then got some losses, and this is where you'll start to see some math, but don't be intimidated by the math, because while you'll have like a whole bunch of different, you can have a whole bunch of different types of loss with a lot of sort of complicated math, in code, this literally will just turn out often to just be 1 line of code. Right? So the frameworks these days help us massively for that kind of thing. We then have optimizers, the bit that actually goes in and updates the various parameters based on the loss that it got. And one of the things I like to say is, you can think of the loss and the optimizer almost as sort of like the automatic part of fixing something up. So if you think about the analogy of a plane flying from Newark Airport through to Singapore here, that plane is not, it knows where it's going, but sort of, 90% of the time, it's actually off course and it's having to correct. So it's constantly doing this sort of correction, and and the autopilot is what will take care of that. Our loss and our optimizer work in the same way, that the loss will basically determine that, oh no, the model's starting to predict things too wrong, we need to correct that and push it back over this way and push these variables this way. And whereas our simple man-made model might have 10 variables for measuring if someone's tall, our neural network model might have like 20, 30, 100,000 or more variables. And the loss and the optimizer basically update this as we go through. And eventually you get something like this, where you can pass in an image, it goes through all these connectivity patterns, it comes out and then it makes a prediction. In this case, that this is a dog in the basket and not a cat. So this is just sort of like a simple way to show you that the concepts themselves are reasonably simple and easy for you to get. So how can you get started? Well, there's sort of 3 skills you want to start working on if you don't have these skills already. The first one would be the basic sort of coding skills. Second one would be knowing a little bit about statistics and data science. And the third one is sort of the machine learning itself. So if you don't code, and I'm guessing that there's quite a few of you on the call who do code, but if you're not someone that codes, then you're going to need to learn to do that. And you're going to find that the language that everyone uses for this kind of thing is Python. And actually that's great, because Python is one of the simplest languages to learn and get your head around quite quickly. The other thing you're going to find is that you don't need to be a great programmer to do this. The idea is you're not trying to build everything from scratch. You're going to be using a bunch of frameworks and also just sort of selecting out bits that you need to assemble your model. So you're sort of learning to code for data, which is actually very different than if you're building a website from scratch or if you're building a mobile application from scratch. So the idea to understand is that coding for data science and for machine learning is actually quite a bit different than, say, coding to be a developer for something. All right, so there's a data science stack that you want to sort of look at, and this is generally the sort of libraries in Python that you would use. You'd be using Python itself. You'd be using NumPy, which is a numerical computing library, Pandas, which is kind of like a library for dealing with spreadsheets and CSV files. Then you've got, things like matplotlib, which will help you sort of plot out things and see what's working nicely and get a sense of, where your models are going. Each of these are actually skills that you can learn the basics of in sort of a day or two. Once you've got that coding, once you've got that level of coding to sort of be able to read the code and understand what it's doing, you find that it's very simple to pick up these libraries. Just as, it is when we come to the deep learning frameworks. Now, there's lots of deep learning frameworks out there at the moment. There's a whole bunch. You've got sort of TensorFlow from Google. You've got PyTorch, which kind of originated out of Facebook. You've got MXNet, which is from AWS. You've got Microsoft CNTK. We're going to say that really you only want to focus on two of these frameworks. So the first one is basically TensorFlow and Keras, which have kind of joined together nowadays. They used to be separate, but they've now, because the creator of Keras works at Google, this has been folded into TensorFlow. And PyTorch, which has come along, after TensorFlow, and is definitely a contender nowadays for one of the sort of two main frameworks. We actually teach in our courses, as we get, in the basic course, we teach people TensorFlow and Keras, but then later on we teach them both, and we find that people can have the ability to pick up both quite easily once they understand the concepts that are going on. So remember back to the things I was talking about earlier on. You've got the four things going on. Right, you've got your data going in, and with your labels, you've got your architecture, you've got your loss, you're an optimizer. This is the whole of that in code. So this is an example of an architecture, of building a fully connected network as an architecture. This is an example of basically passing in an optimizer and a loss. Remember I said that often they're just one thing that you'll pass into the framework. You don't need to know the math for doing, for using these. And then you've basically just got it to train. So we pass in the data that we're going to have, and then the labels that we're going to have, and then this will basically train it for us. So very quickly, you can get up and running where you're actually building models and making this stuff happen. That's that's some of the key things that I would sort of say. The TensorFlow can be really good, because you're actually getting a TensorFlow ecosystem rather than just one sort of framework. And PyTorch is gradually becoming like this over time as well. So in TensorFlow, you have the main framework of TensorFlow. You have what's called TensorBoard for evaluating models and looking at how things are going. You have TensorFlow Lite. If you wanted to deploy a TensorFlow model on a mobile phone, great. You just convert it into TensorFlow Lite and then put it out. And you wouldn't need to rebuild this from scratch. This would basically have everything you need to convert it to put it on a mobile phone. If you wanted to put it in a browser, you would use TensorFlow.js and convert it there. Right? So this ecosystem gives us a whole bunch of things that we can kind of think about. Right? So I'm looking at there's a couple of questions. So how do we visualize the data in multiple dimensions? That's right, that definitely what we're using, what we're thinking about is going to be multidimensional, and we'll use things like matplotlib to visualize different elements of it. There's a whole bunch of tricks. Certainly TensorBoard is a great one for being able to visualize the data, whether we're working in images, whether we want to see what's actually going on with those variables and the weights and biases in our model. We can see that kind of thing as well. To finish up, I'm going to sort of say, okay, remember, your goal is to be sort of an implementer at the start, not a researcher. If you can learn to build these models and put them into production and you go through all those things, you will be able to get jobs in this industry because there's a desperate need for people looking for this. I would say that what you really want to do is start with an application you want to build. When Martin and I are teaching courses, we always set people, okay, we want you to come up with your own project. we don't want to dictate what you should be doing, because often you're going to have individual domain knowledge which is unique to you. Then the other things I would say is realize that this field is huge, right? It's too big for anyone to know everything in the field, and it's growing day by day. I think when we were first getting, certainly for me, when I was first getting into deep learning 5 years ago, at that stage, I was lucky if there was one article a week that came out about this, right? Nowadays, there's probably 50 to 100 a day that are coming out about this sort of thing. And if you get stuck, just go back to the building blocks. Remember that every model will have an input and an output, the data. Every model is going to have an architecture, every model is going to have a loss, and every model is going to have an optimizer. If you think about these things, you're certainly well on the way to being able to learn this stuff so that you could go out there and get a job doing this. So I'm going to pass over to Martin. And Martin's going to go through some nice examples and show you also some more interesting info. Oh, we had someone pop up.
Okay, so you're happy for me to take over now?
Go for it, yes.
Okay. So can you see my screen now, Sam?
Everything great.
Okay, so I'm just going to talk pretty much about the same thing. Sam and I always kind of do our teaching things as a pair. So it may be that my stuff is a repetition of what Sam has said. On the other hand, maybe you kind of like my explanation, and then typically we find even having the same thing twice is helpful to people. So just like Sam, I'm a Google Developer Expert for machine learning and deep learning. We were one of the first cohorts they took on globally. I also help organize the TensorFlow and deep learning meetup. Unfortunately, we haven't yet had a COVID online meetup, so we plan to do that soon. But typically we'd meet up in Google. We'd have quite a large crowd turnout. We just need to figure out how to re-engineer this for the new world. My background is in finance and machine learning. I spent a long time in New York doing kind of the quant finance thing. But now I kind of switched hats. After the financial crisis, I switched hats. I decided, okay, I should do machine learning because that's really kind of my passion. So I do kind of on the research side of Red Dragon AI. So my quick outline is I'm going to talk about some of the kind of practical AI basic stuffs and some key ideas, and also show you a concrete example, which is something that one of our students from the online course, so from our essentially the beginners or the Jumpstart course did. And then I'll talk a little bit about text models and kind of the pace of change. But hopefully I can introduce all of this, through all of this, to give you some idea of where the jobs are, and it's not all about building the model specifically. So let's just go into some little basic ideas, and then hopefully this will introduce where the different roles are simultaneously. So back in, in the, I think it's like 2007, 8, that kind of time frame, a competition was created called ImageNet. And the overall goal of this competition is to categorize between 1,000 different things in the images. And in the things, there's kind of tons of breeds of dog, but also airplane, lamp, kimono, tusker. Tuskers are kind of elephant. So there are 3 elephant types in this data set. So there's a whole bunch of different things in images. And the training set for this is millions of accurately labeled images. So that they've gone online and got groups of people to rate each image for all the different categories. So they're pretty sure that the training set's good. Even though some of the training sets there may be 2 things in this image and they chose 1. Okay. But the goal to do this competition is to make a model which can predict for an unseen image, what class should this be? And the kind of the metrics that people would use is they would measure the top 1 accuracy or the top 5 accuracy. So did you get the first guess right, or is the correct answer in your top 5 guesses? So this is kind of the competition, and quite a few academics worked on this, and quite a few corporations worked on this, kind of all in competition with each other. So every year there'd be like a new winner. So how do you win this competition? Well, since 2012, building a deep learning network is the way to win, because this is suddenly the deep learning thing like rose as being like the most effective way of doing this. So instead of building whole bunches of rules about how to classify an image, you just let the network learn all on its own what rules to implement. And in order to go from one year to the next, because every year it's getting better, people would vary the different building blocks that were being used. So there'd be innovations in terms of the little boxes in Sam's Inception v3 thing. And they'd also vary how these interconnected together. But also people would train these. So they would use GPUs. This is NVIDIA, typically NVIDIA graphics cards, or Google created their own custom silicon called TPUs to do these, to train these kind of models, and also to use the models once they're trained. So Google has invested a huge amount of money in their own silicon so that their server farms can be super efficient. On the other hand, if you wanted to do it in the cloud, you can either use the Google Cloud, which has got TPUs and GPUs, or say Azure will have GPUs, or Amazon, or they're really specialist kind of GPU people. Anyway, training these things is no small feat, because to get better and better results, you're going to need bigger and bigger models, or have some more and more interesting ways of treating the data. And so, people discovered that very quickly you need to do training at scale. However, in terms of achievements, now these models are better than humans. I mean, since like 5 years ago, these things have been achieving better scores than any individual trainer of these images. You basically now need a committee of people to give a label in order to be competitive with the machine. But the other thing that people found was this last thing, that these ImageNet winner, or even a pre-trained ImageNet network is actually useful for problems which are not ImageNet. So that's kind of something which is kind of surprising and super useful. So in order to leverage what the ImageNet competition gave us, which is these big models, what we're going to use is we're going to realize that building and training this full ImageNet model is very expensive. Okay, but what the big corporations will do typically, and also academic labs, will give away their trained models for free. Now, in two senses. They'll both be free in dollars, so you don't have to pay for the models, but also free as in freedom, in that the license allows you to do whatever you like with your models, right? Or their models. And so this is I'm a proponent of this whole freedom thing for open source software. So basically it gives you the license allows you to do many, many things, just taking this on board into your company and using it. No problems with IP. But the key thing is for these models is that they've kind of learned to see. So in order to do the 1,000-way classification, they have actually learned to understand, well, what are the important things in an image? What does fur look like? What does a tusk look like? What does a wing look like, whether it's an airplane wing or a bird's wing? Okay. However, what you find is that even on unknown classes, so it's something which isn't in the top 1,000, these 1,000 classes it's trained on, the models will be consistent. So suppose it's been trained on tortoise, so it knows what a tortoise is, and it knows what the sea is because it's seen lots of fish. If it sees a tortoise in the sea, it can learn that it's a turtle, right? So if it just thinks it's a cross between a tortoise and a fish, it will do that consistently if you show it a turtle. So that consistency allows you to reuse an ImageNet model on your own task. So you can basically you can train a model on top of ImageNet and use the fact that it thinks this is a tortoise fish to say, okay, all of my turtles get labeled tortoise fishes, I can use that as my output. So for the new model, we're going to take our images, our class labels, which could be any kind of vision task, definitely not constrained to animals, anything to do with something that the ImageNet thing may have learnt to accomplish our task. So I'm going to show a quick example of this, and this is from a student from our Jumpstart course. It's a nice, the reason I'd like to show this one is because it's a nicely laid out project. It also has kind of good local flavor in Singapore. On the other hand, we should emphasize that everyone gets to choose their own project. We don't force people to like do the coursework and tick the boxes for the project. Basically, we're open to, if you have a startup with your own goals, we're happy to help as part of this project. Anyway, so, and I mean, no disrespect to the student, but I'm not going to say that I only picked the very best student we've ever had. This is a project which is totally doable and by people who attend the course. He's done a good job though, in terms of making it so that you can see what's going on. So this is a chicken rice classifier. And basically what the student had found was someone's, I think it's an Instagram feed, where someone had every day in Singapore, they had eaten chicken rice and taken a picture of it and put it on their feed. And so this gives us a data set of, I guess if he's actually loading up the steamed training set and the roasted training set. So we've got, well, this is maybe 400 images of steamed and roasted chicken rice. So he's loaded those in. He's made these into data frames. Basically, there's some kind of, this is handling the data set. And basically, it may look complicated in code. On the other hand, during the Jumpstart course, we also have a bunch of notebooks which illustrate how you would handle different types of data. So, you know, particular data set may be a bit tricky, but there's probably something which is pretty close, which will help you on your way. And so here's some nice examples. Clearly, we've got some steamed and roasted chicken rice here. So we just like to see what the training set looks like to see how difficult is this. And I guess one of our key AI points is if you can do this task in less than a second, then it's probable that an AI, like a trained machine, will be able to do that task, which actually will cover a very, very large number of professions, which is why people need to get AI ready as soon as possible. Anyway, I can tell the difference between these two chicken rice pretty easily. Therefore, yes, I'm pretty confident that this whole model is going to work. So what the student then, Jason Tan, then did is he took a NASNet mobile model, loaded it up. So this is all for free, just downloads. And then he made up a, basically he's replacing the last layer with a fully connected network. So this is kind of, there's some detail in there about how this whole, what's called transfer learning works. But he's got some more data set stuff. He then takes the output of that, takes the head of the base model and then does some extra layers of his own. And then, you know, and what you get out is a very, very big model. But most of these layers are not his layers. Most of the layers are the pre-trained ones, which is downloaded. So having done those, these are lines just like in Sam's slides. I'm going to take an optimizer. I'm going to compile my model. I'm then going to fit it to my training set. And basically, this is showing the training going on. You then can just save the model. And then having done that, basically, we can have other components which will load in the trained model and then use it. So one final thing is he just did a test. He's tested the model on some internet image that he got. And so he's found some, this came off probably Google Photos. He's got a picture of rice and it's come out that this thing believes it's steamed. So this makes total sense. He's done, in terms of a project, nice job. And it may be not that surprising that you can classify steamed rice versus steamed chicken versus roasted chicken. On the other hand, if I were to give you a picture and just say, well, from the pixels, tell me the difference. Now, maybe they're slightly different colors and stuff, but basically, if you're going to write a set of rules to do this, you've got a hard problem. But this is learnt from scratch, or using that basically from scratch in terms of the training on top of the ImageNet model, which has had millions of dollars of development put into it by someone else. This is learnt to do a hard task, with rather little data. He had like 400 images. So let's continue on. So Sam, can you see my slides again?
Yes,
Yes, fantastic, okay. So just a quick little more stuff about images. Sam, or hardly anything. Sam had pictures of images in his presentation. It showed kind of, you know, the different kinds of things you might do with images. Here's another thing you might do with images. This is like classifying, like where is the road, where is the pavement, where are the trees in general. So this is a kind of a different kind of task. But on top of this, there's a whole bunch of other image tasks that you might do. Sam showed the colorization task, but there's also counting things, like you might want to know how many people are in a queue. Facial recognition. Someone mentioned 4D. I would say yes, predicting 4D's not, we would say don't try and predict 4D. One thing which I would say about facial recognition here is it's actually got, it's not just a surveillance state kind of thing. For instance, in Vegas, casinos are charged with stopping problem gamblers from coming into their casinos. So much so that if a problem gambler loses a ton of money, they could then turn around and sue the casino for not having prevented them gambling. So there's casinos really want to stop these problem gamblers by force of law. So what they will do is they'll actually do facial recognition to try and spot people coming in who might be a gambler that they really shouldn't be serving. And so while you may say, well, let's try and predict the 4D, that's one application. On the other hand, on the flip side, many companies want to do tasks which you can only really do with these kind of computer vision things for reasons you might not have thought about as a customer. Anyway, let's continue. I guess the other thing is we've had people coming to our Jumpstart where they've had some task to do with, you know, quality assurance on detecting the sealant coverage, and or maybe it's, you know, imperfections in silicon, and all sorts of different things are a computer vision task, and they've come away like they've been amazed at how quickly they can get to a deep learning result when they've spent, you know, years on using kind of old school methods.
So Martin, we've got a question that, just to follow up on that. Someone's asking, what about share trading or automated trading run by well-funded hedge funds?
Okay, so I guess that my point there is we will tend to pour water on people wanting to do automated trading, partly because you know, these well-funded hedge funds have already got systems to do this. They're keeping pace with the academics and the, you know, and the Google, except they're not telling anyone. So in some sense, if you hear about a technique, its usefulness has already been exhausted. So there was a period when reading Twitter would tell you like what the good picks would be, or looking in supermarket car parks via satellite images. These are all kind of signals which were surprising when people heard about them. On the other hand, by the time you've mentioned them, a lot of the value of that signal has gone away. So we at our Jumpstart course, we will often have people who want to predict the stock market, and we'll try and steer them away from it. It's kind of like in Singapore, it's almost like a problem gambler situation. Predicting the stock market is such an attractive target. So many people do it. It's super hard to do because, you know, there have been millions of people in groups predicting this thing for hundreds of years. This is going to be tough unless you're at a well-funded hedge fund who already has systems to do this, when they probably are already, you know, dabbling or using deep learning in the first place. This is not an amateur thing to get into. On the other hand, if you're an amateur and you want to detect cancer in scans, that is totally doable in terms of something an amateur can approach and get good results or surprising results. So this is something where, you know, surprisingly, you might say, shouldn't you be curing cancer rather than doing finance? Actually, curing cancer is kind of probably the easier thing, because cancer is not learning from your models as well. Whereas the financial markets will learn to try and beat you as soon as you've implemented anything. Whereas cancer is too slow moving in some sense to get away from finding it on the scan. Anyway, slight digression, but hopefully that kind of sets the scene. In the courses that we run, in particular Jumpstart, we don't want people thinking about financial markets if they can help it. They might not be able to help it, but you know, there are many other lower hanging fruit. Okay, let's talk a little bit about text. There are lots and lots of text tasks, like is this product review a good review or not, right? Or is it spam, right? I don't want to include obvious spam, or maybe I could have a fake news detector. I don't want that in my feed, or I don't want that on my e-commerce site. I also probably want to detect, well, what does this customer want if they're starting a chat, or has a message. Maybe I want to understand their intent. Or suppose I'm looking at news. I might want to extract what names were in that news article. But I might also want to know exactly who was mentioned in that news article. I might want to know down to, like, is this just a Barack Obama, or is it the Barack Obama, right? So and you can do that for millions of entities. So that there's many tasks in Singapore are not so much the vision tasks for a production process, but also the production process in Singapore is also heavily orientated towards text processing. There's many people in, we would normally say many people in these office towers doing what are essentially text processing tasks. And if they can do that in 1 second per thing, like identifying stuff written in a form, that should be a target for being automated away. So this is where being on the side of automation will definitely be a benefit. So here's a quick example. Feedback urgency. Suppose I've got a whole stream of feedback coming in. Some of it's positive, some of it's a bit negative, and some of it's really negative. I want to be able to classify this. And so I want to be able to say for any message, which one of these three is it? And the goal is probably not to tell the difference between positive and mildly negative. The important thing, well, it depends on who your manager or what the task is, but it may be that I want to identify what is urgently negative, because I would probably try and launch some kind of customer help thing on this. And rather than have my customer service desk reading every message as it comes through, basically, I would like to highlight this, and I color it super red in the box, saying this is urgently negative, you need to deal with this. And so the actual goal is not just to kind of evenly detect which one's right, because it may be these two are the vast majority of the data, but this one, I never want to miss one of these. So the actual goal may be not just prediction accuracy. I want to know, like, where am I going to lose money? Then we're going to need to make a data set. So I'm going to have to get a whole bunch of these feedbacks and then label them. Or maybe I could fake the labeling by looking at what happened once that message was received. If that message caused someone to make a call, then maybe I could soft label that as being urgent. So there's thinking about the process and how the actual system works now with humans is also kind of important. So from a research point of view, I would love a data set which just came along and told me what's what. But the reality is, in a commercial setting, there may be all sorts of hints and like systemic things which tell you about the task, which is not just a clean data set, but there's lots of, it may be that you already have hundreds of thousands of these weakly labeled feedbacks. And so that you don't really have to do any hard labels with a team which labels things. So knowing about this is slightly different from making a model. And so anyway, let's move on a little bit. I guess the question is, can we leverage other models? Just like for the chicken rice thing, we used ImageNet pre-training. Can we use other models? And so the answer to this is yes. And so since basically this BERT thing is the key thing. So word embeddings came along in 2012, but BERT, which is a model you might have heard of, or the GPT models, GPT-3 being the latest, since 2018, this whole thing has kind of changed how natural language processing takes place. So these kind of dramatically improved kind of insights into text, and just like the ImageNet model has kind of learned to see, these things kind of learn what text is about. And this enables us to reuse the BERT model, for instance, to help with our task. So just as an aside, I mentioned that for ImageNet, we had 1,000 classes and we had millions of training examples for, classified images. To train BERT, it's slightly different. What you would do is you take a very, very large amount of text, and the trick is to just mask out words in that text, and then use BERT to try and guess what the word should be. Now this is kind of, this is called unsupervised training, just because it's not like we have labeled text. The text is in a way its own label, and the idea that I should be able to guess a masked out word is kind of unlabeled, but I do know the right answer because I've got huge amounts of text. So basically to train BERT, you would take like sets of novels or Wikipedia or Reddit comments or basically the web crawl, and you would do this kind of fake kind of task of replacing the masked word, or sorry, predicting what the masked word should be. And then, just like the ImageNet model, instead of taking this piece, which is the output that I've been training for, I'll take that away and now replace the head on top of this BERT with my training task. And so Google, and others have essentially given away their structure and their models so that you can then take their expensive training and then put your own task on top of this. And so this thing will be used to kind of understand the text. I don't care about replacing masked words. I only care about my thing and how what it knows about my movie reviews or my feedback. Anyway, so in order to do this feedback thing, I'd take a pre-trained BERT model. I'd use the annotated data we have, and I'd still need like hundreds of examples, but not millions of examples. I'd train a new head for the BERT model, and then I can deploy this as an API. Okay, and typically as an API, I want to deploy this in a streaming way, right? So the stuff is coming in, I annotate it, I can then message people, but basically the model then just becomes a component in a much bigger system. But then, in terms of the humans in this, there may be other pieces in this, in that suppose it starts to mislabel some things, or a new kind of urgent feedback comes in. Suppose I trained this model in 2019, and 2020 comes along, there's this whole new word, COVID. Now maybe I have some urgent message regarding COVID, which need labeling, that I need to make it so that my model can be adapted for new stuff coming in. So not only will I have a previous model, but I'll also be able to have a new model with the new terms come in, and I'm then going to want to see, well, have I lost anything by learning about COVID? Did I forget about the flu, for instance, or whatever the urgent issues of the day are, right? So basically, you've then got a versioning issue. You've got a human in the loop kind of issue. You've got a managing people and managing what the customer service reps are seeing. There's all sorts of things to try and make this an ongoing process, rather than the raw, take a training set, learn the model, we're finished, right? So this is kind of illustrating how these things kind of where the jobs are. So there's a nice diagram from these called the Skills Framework for Infocom Technology Career Pathway. I guess we'll put a link to this in the notes. This is page 1 of this, but this is the one related to data and artificial intelligence. And some serious people at the IMDA or one of the government branches in Singapore have actually pretty well annotated where all the different people lie in kind of structural boxes. But let me just kind of explain what some of these jobs roles are. Now, clearly, the research thing, if you're a researcher who's been using machine learning, or like a physics person who knows some programming and understands data science, this is obviously where you can provide value. But you have to understand that just having great academic results is not the same as being able to put this into practice in industry. And so this is where the industry research, there's a slightly different focus. If you're a developer, Can you pick up practical AI skill set? Yes, we'd say this is very doable. If you program professionally, then this is absolutely a doable thing, because you're probably thinking in terms of programming, you're definitely got the skill set. On the other hand, the data side is a bit different from what you're used to. And so this is kind of where, this is a different kind of reskilling. If you're an engineer, so in one of these boxes, there'll be things to make these systems work. If you're into cloud or servers, you need to think about, even once you've got a model which has been provided by the researchers or the machine learning developers, you'd also want to be able to put it into production. So you're interested in reliability and fallover, or scaling, versioning, clustering, cost as well, because running these GPUs is not cheap. So you need to be able to keep all these things in balance. And so there are jobs in all of these areas. Understanding how the models work is one piece of this, but also understanding what resources they're going to use is another. If you're kind of in the mobile field and want to apply this stuff into mobile, you need to think about, how are we going to make this model, which is some expert has produced? Well, the BERT model is not something you're going to want to put on a phone. That's a big model. So you're going to want to focus on, how do you make it smaller? How do we make it so that you can do images in real time? Also, what about privacy? Are we sending stuff up to the cloud? Or is it possible for us to use our mobile models and still send up something useful to the cloud without giving away the person's identity, for instance? So there's a lot of kind of ancillary roles around these models, which are very important when it comes to industry. Okay. If you're an analyst, maybe you've been working with spreadsheets and SQL or visualization, I would suggest that you should definitely be thinking about upskilling to have these kind of machine learning techniques as well. And then you'll be able to kind of leverage your domain expertise into this couple this with machine learning. So rather than being, in some sense, a passive component, you could be actively driving some of the innovation. As a manager, it's kind of important to understand how kind of the machine learning thinking is different, and also understanding, and this is, I would say, in Singapore, understanding how managing a research team where people genuinely don't know how long things will be or how it will work, whether it will work, they want to explore. This stuff is very different from being implementation specific, saying, well, I need these results in 1 month, and it's going to be 4 days from this person, and these 2 teams will work on this. The implementation thing, Singapore's got down to an exact science kind of thing. On the other hand, the research thing, it's not that people can produce research on demand. It's, they can try on demand, but you have to understand that this is a different kind of animal in management terms. Okay. So I'm going to do a quick advert for our courses, because unless someone stops me. Basically, we have a set of 5 courses at the moment covering different aspects of AI. These are held in conjunction with SG Innovate. And partly through that, they've got significant funding available for Singapore citizens and PRs. So there's an IMDA or CITREP funding scheme, which allows you to reclaim the vast amount of, or the vast majority of the funding for this, particularly if you're mid-career, or reskilling or whatever. And so if you look at this SG Innovate Talent Development tab, you'll be able to get a whole lot of information about that. I guess, but for this crowd, I should probably say that there's this Jumpstart course where basically it's 2 weekdays, which are kind of face-to-face, and we'll do this online now, but basically you can interact with us at any time. There's also videos and questions, but also there's a pick a project. It's not really pick from our projects, it's basically pick your own project. And we're kind of, if you've got something that you want to do, then that's brilliant by us, and we'll try and make it so that that can be your project. And with all this, you'll get a certificate, etc. So prerequisites, most participants already do some programming, or at least have got a feel for what programming it is. I would say that the Python element isn't super difficult, even if you've been programming in a different language. In some ways, There are enough examples that it's a copy-paste kind of exercise with some, you have to think what you're copying and pasting, but basically this is not super hard programming-wise. On the other hand, to understand why you're doing things, maybe that requires something. Basically, you've got to be willing to learn, on the other hand. If we've definitely had participants who'd say, well, we've always done it this way at our job. And we would probably say, well, let's try and think of another way to do that, because this deep learning stuff is very different. And maybe the deep learning can be combined with your what we would call old school methods into some kind of best of both worlds thing. On the other hand, it may be that this machine learning thing actually picks up what you do in the old school pretty quickly. Anyway, so yes, pretty cool, because it's some programming will be very, very helpful. We have had people who haven't had much programming at all, but definitely a willingness to learn is important. From there, once people have got familiar with the core concepts and making things that work, so all of these kind of require that Jumpstart course, unless we give like a special exemption. We've got a thing on advanced computer vision, so this will be all the computer visions which we've mentioned between us. We'll cover in that. The advanced natural language processing, this is a super up-to-date course. We know that there's no one else out there teaching this in class. So this is super up-to-date. Self-supervised learning, this is taking the whole unsupervised thing. This is it's a super hot area of research. This is definitely, if you've got your research hat on, Model 5 is more like if you're an engineer and you want to serve these models on servers or on mobile, or you want to understand how data science is managed as a process, this is what the production course is. So typically if someone has like a computer vision task they want to do, they'll take the Jumpstart and the computer vision, and then they do the production. So that would be you don't have to do all of the courses, but you can kind of pick and choose. It may just be you want to do the Jumpstart and then the production one if you're in management, say. Anyway, this is something which SG Innovate will be happy to fill you in on, that they handle the money side and the organization side. We just turn up and do the courses and look at all the projects. So in conclusion, being a developer is already a key skill. If your mother wanted you to be a medic or a lawyer, which is entirely possible, but not a developer, actually now, actually developers are pretty cool, and people should be cool, be a developer. Anyway, totally reasonable to add deep learning as a skill set if you're a developer. But there are other skills required in all this. Basically, there are lots of engineering roles to keep these models alive and to keep it all ticking over at a decent return on investment, super important. Data roles, just labeling an image isn't tricky, but labeling some text, well, labeling isn't tricky on its face, but it starts to get tricky because it's the odd cases which will always catch you out. Training gets tricky for text, where it may be like, is this post fake news? Yes or no? That's going to be a super hard task to detect, to even understand whether this is the right question to be asking, right? So the data roles is not just about training the model, but there's thinking about what am I really being asked to provide in some sense. And then strategy, like where can this AI be applied? How is the process going? Are we kind of meeting milestones quickly enough? All this kind of thing. There's a whole bunch of different roles. And I just say that overall, this whole area makes a lot of kind of strategic sense for Singapore, just because as a data hub, and you've got a very good skilled set of populations, higher skilled than most places. You've got great data pipes. You've got privacy law, which makes sense. You've got a whole bunch of good elements here. And so making this like a data science hotbed makes a great deal of sense for Singapore. Anyway, with that, I guess I'll say that we can do some Q&A for Sam and I, or I could move on to, we could let Samantha, the MC, kind of roll us out.
All right, thank you, Martin and Sam, for the very insightful questions. If you guys have any other questions, do feel free to type it in the chat. But we do have some time for a couple of questions. And there's one question in our chat that asks, do you have any thoughts about platforms like Azure ML, AWS ML, Google, etc.?
Sam, do you want to?
Yeah, I'll take it. So the funny thing is, okay, of course we're associated with Google, and we're very lucky that we kind of use a lot of Google services for free. So we certainly know GCP or Google Cloud Platform very well. That said, I would say we're also reasonably platform agnostic in that nowadays all the big platforms are basically supporting this kind of thing. Just yesterday, Martin was sending me something really interesting that Azure is going to be introducing on their platform for training models really quickly. So you kind of want to have your thinking be platform independent, much more than say before when in the mobile first era, certainly AWS was the one that you wanted to know and everything was sort of built around AWS. Nowadays, they're all kind of becoming very similar in their sort of thing. So often it will depend on what your company chooses to use, some of that. It's really more about knowing the fundamentals of how this stuff works and how to build the models. And then you'll find that, you know, like we talk about in the production course, the deploying something to AWS versus Google is very, very similar nowadays, especially with tools like Docker and things like that. It's all become, you know, a lot easier than it was 5+ years ago. That's for sure.
On the other hand, I should pipe up that during the course we use the Google Colab notebooks, and so Google has this Colab which I showed for the chicken rice thing. You can get a GPU for free or a TPU for free while using those Colabs, and it kind of times out after 12 hours. On the other hand, if you don't have a GPU, you can always get resources for free there because you can log back in and to the service and get a new one. So that's a super helpful thing that Google will do for anyone. And also, Google's the only game in town when it comes to these TPUs, which are like super fast. So if you can get it so that your framework uses TPUs, that's a great thing. Anyway, so we do have a natural bias in some sense. We kind of backed Google as the horse because we like TensorFlow, and also they got the cool toys. So you know, so we have some bias, but it's not that they pay us any money. So there we go.
All right, thank you, Martin. One other question. Right, let's just take a look. While we are at it, can we just show the link to the feedback form? So while people are listening to the Q&A, they can actually complete the feedback session. All right. So this question is, how best can we make use of our certification to get a job?
Should I take that one?
So I'm not sure. We can't say that the certification will get you a job. We do know that quite a few of the SG Innovate summation students who are getting accredited in some other way, and we also know that we've had people from all walks of life, and but basically government departments, people doing from academia will still gain quite a lot. The certification we give is partly because we know that Singapore likes certification, that we do that, but it's not. We also don't want to say, okay, a job comes with a certificate. On the other hand, as an employer, if I see someone coming in and I see that they had bothered to do something for themselves, that's a good sign. So it's just proving that this is actually proof that you've gone out and done something which is relevant and useful. And if they look at what we're teaching, they'll see that. So, and right. This is also why we get people to do their own projects, because coming up with your own project and doing it as an individual is very much more, is super easy to detect that in a job interview. If you just say, well, I did a team project when I was at NTU or something, as an employer, I kind of have to assume that you're the person who fetched the coffee while someone else did the work. Whereas with these individual projects, you can say, okay, you did it. It may be you monitored whether it was your cat that was coming in the cat flap. But even so, that proves that you really knew about that project. And so
the big thing that we've seen over the past couple of years is that employers want to see that you really know how to build something. So one of the things we encourage by forcing you to do a project is to sort of build up a nice portfolio of projects. We've had students, one of our students from the 2017 batch went on to be a director of AI at one of the big four consulting companies, and then now is sort of is working at Element AI, one of the top sort of AI startups in the world that's basically helping run their Singaporean office. And so he started out as someone who knew the basics of coding, was working in a bank, wanted to make a career change, took the course, was very active in the course and built a bunch of things, and then used that to leverage a number of different jobs as he sort of went up. And that's something that we kind of see as a theme, that the people who tend to do really well are the ones who end up building a nice portfolio of a variety of different things that employers look at and say, oh, that would be useful to us. That would be something that we would want to be able to do in our company.
Yeah, I fully agree on that, and I think just jumping in as a talent development side of things, I do agree that a lot of times when we look through CVs, we look through resumes, we really look at additional things that you do, including the projects that you've done, even hackathons or other things that you've completed other than your degree and your work experiences. Now, I just want to thank everyone for joining us on this session. I think 1.5 hours flew by just like that. We've come to the end of today's workshop. Please help us to fill up a short survey in the Zoom chat box before leaving. Upcoming, we do have our second workshop for today upcoming, and it's Introduction to Cybersecurity, What's the Hype? So if you're interested in venturing into the cyberspace, the workshop link will be in our main lobby itself. Thank you, and thank you again, Dr. Sam and Dr. Martin and Sam. I really enjoyed the workshop. Thank you, everyone else, and enjoy the rest of the conference.
Okay, thank you.